The flexible acoustic contact lens's capstone goal was to target the large market for non-invasive ocular therapy, given the amount of people with visual impairments. To do so, we researched flexible miniaturized transducer devices to put into a contact lens made of PVDF due to their ability to conform to complex shape geometry such as the eyeball. The first application found is photoacoustic imaging to map ocular vasculature, which can lead to the application of photomediated ultrasound therapy. The goal of photomediated ultrasound therapy is to ablate the blood vessels to restore normal flow. Another application that we discovered was deep brain stimulation through the eye. Photoacoustic imaging allows for deep brain stimulation because it can penetrate deep enough to reach the retina and ocular vessels. An alternative design for our product was influenced by using lithium niobate as a material for the contact lens. This material was eventually ruled out because PVDF has the superior photoacoustic properties, flexibility, and a more reliable fabrication process.
In COMSOL, we modeled the PVDF transducer with a parylene C matching layer. The space dimension for this geometry was 2D axisymmetric, and the physics of the simulation were pressure acoustics, solid mechanics, and electrostatics. The solid mechanics physics was applied to the PVDF, while the other two physics were applied to everything else. In the image shown for results is the 3D plot of the sound pressure level in decibels. The results for this pressure distribution in the medium would look the same as this one. However, the sound pressure level plot is just easier to visualize. Overall, the COMSOL results show the focusing effects of the curved PVDF for an application like photo-mediated ultrasound ablation. For the SolidWorks modeling, we created a contact lens shape that the PVDF would be shaped into. The diameter and base curve of this model are shown in that section. The modeling team was also able to experiment with a software called PiezoCAD, which is a tool for rapid iterative transducer design application. The thicknesses for the transducer matching layer were the same as set in COMSOL. However, the software did not allow for us to test a curved design. Overall, PiezoCAD allowed for us to see the impulse response from a two-way pulse echo. We also tested lithium niobate as a transducer since that was our alternative.
Our first lithium niobate transducer was used as both a practice and a reference transducer. We used this lithium niobate transducer as we were familiar with the characterization and compared it to the PiezoCAD results to conclude that PiezoCAD did in fact deliver accurate characterization data, meaning that the PiezoCAD data of the PVDF would deliver very similar to real-life characterization experimentation results. For the PVDF fabrication process, we shaped the lens by applying heat and pressure to the PVDF using a steel ball that is the same shape of an eye. We then cleaned and attached the wires and the ground ring as shown in the last photo to conclude the fabrication process. To obtain the phantom eye model, a 3D eyeball mold was printed using resin. This mold was then filled with colored 1.5% agar solution and allowed time to solidify to be used for further laboratory testing on the fabricated lens.